2.78 trillion parameters, the largest set of open weights anyone has ever published. And there is now an engine, 6,000 odd lines of C, no Python, no CUDA, one binary, that runs it on an ordinary laptop. Not a distilled copy, not a pruned one. The engine's own validation suite checks its output against a reference implementation of the real model, layer by layer, and the final numbers agree to the 6th decimal place. Whatever comes out of this thing is what the original would have said. The memory floor to open it is just over 29 gigabytes. Machines with that much RAM are sitting idle in a lot of homes right now. So that's the claim, and it's true. And if that were the whole story, this would be a 5-minute video. It's a 22-minute video because of what I found when I downloaded the engine's entire repository this morning and actually read it. There is a table in its documentation that appears to be printed backwards. 4 measurements, same machine, same model, 1 variable changing, and the results run in the opposite direction from everything you know about computers. The author measured it, published it, and explained it in 2 sentences that I think are the most useful thing you'll hear this week. And further down the same page, almost as an aside, there's a second result that nobody's headline mentions. And it's the one that turns this from an astonishing stunt into something you might genuinely use. Here's the plan. What this engine actually is, and the frankly delightful way it's distributed. The split that makes 29 gigabytes possible, including a sentence of fine print that corrects every headline about this project, including, in fairness, the number in my own title. Then 1 token's journey through the machine. With arithmetic I did myself that puts a hard physical ceiling on this whole approach. A ceiling no software update can move. Then the backwards table, then the part of this repository that impressed me more than any benchmark. How these people document their own mistakes, including one they shipped a fix for today, then the buried result, and honest limits of which there are plenty. Standards note. Every number in this video is either from the project's own published documentation, which I pulled directly this morning, or my own calculation, which I'll show. Let's go. What this actually is. The engine is called Waste. Yes, really. And it comes from the company behind SQLite Cloud, which is a detail worth pausing on. This is a database organization walking into machine learning inference. Hold that thought, because the entire design turns out to be a storage design, and it shows. It's written in C with no third-party runtime dependencies at all. Their documentation is explicit that Python and PyTorch are needed only to convert and validate models. Quote, never for inference. You compile 1 binary, you point it at 1 container file, and that's the stack. The model is KIMI K3, 2.78 trillion parameters, published weights totaling 1.42 terabytes. The engine converts that into its own container format, which lands at 982 gigabytes on your drive. And here's the detail that made me smile. The converted container is distributed by Torrent. There is a magnet link right there in the README, a frontier-scale model, moving around the internet the way large files did 20 years ago, peer-to-peer, no account, no gatekeeper. I genuinely can't think of a better one-image summary of what open weights means in practice. Nobody can revoke a magnet link. License on the engine, Apache 2.0. The model's weights carry their own terms, read those separately. The split and the fine print every headline skips. The architecture in 1 sentence from their own README. Keep the model's trunk in memory, stream the selected experts directly from disk, and use whatever RAM is left as a bounded expert cache. Unpack that. K3 is a mixture of experts model. The network is built from hundreds of specialized sub-networks per layer, and for each token, a router activates only 16 of them, which means at any given instant, the overwhelming majority of those 2.78 trillion parameters are doing absolutely nothing. Idle parameters don't need to be in memory. That single observation is the entire product. Everything else is engineering. So the engine divides the model in 2. The trunk, the parts that run for every token regardless. Attention, routers, embeddings. The output head stays resident, compressed to 4 and 8 bits, at 27.28 gigabytes. The experts, the vast bulk, live on your drive at 3 bits each. Fetch the instant the router names them. Trunk plus a working cache for the conversation gives you the floor, 29.06 gigabytes at 4,000 tokens of context. And I like this detail. The engine refuses to start below that floor. It won't limp, it declines. That is unusually disciplined behavior for a piece of software, and it's the first hint of the engineering culture we'll get to. Now the fine print, and I'm going to read it to you nearly verbatim, because it corrects every headline about this project, including mine. Their documentation says, for K3, 64 gigabytes is the practical minimum. A 32 gigabyte machine can open the model, but will page heavily. So let's be precise about what's true. 29 gigabytes opens it, 32 runs it badly, 64 runs it as designed, and on their 64 gigabyte test machine, the engine automatically assigns itself about 46 gigabytes, most of the difference going to that expert cache. The gap between opens and runs well is where every exciting headline about this project lives, and the author didn't hide it. He wrote it in plain language in the second section of his README. The headlines just didn't read that far. One more piece of honesty from the same page. That 29GB floor is measured at a short context. Push the context window up and the floor climbs with it. The famous number comes with a short conversation attached. One token's journey. And the ceiling nobody can move. Here's what happens every single time this engine produces one word. The token enters the first layer. Attention runs from the resident trunk. The router examines the result and names its 16 experts. The engine reads them off the drive, and their container is arranged so that one expert costs exactly one aligned read, a layout decision that a database person would make instinctively and that matters more than any amount of clever threading. Then the next layer, and the next, all the way down the stack. Total damage from their own documentation. A cold token reads about 17 gigabytes of experts from your drive. Not per prompt, not per session. 17 gigabytes per word. Now let me do the arithmetic that number forces, because it defines this entire category of software, and it's mine. Check it. If one token costs 17 gigabytes of reading, then one token per second requires 17 gigabytes per second of sustained read from your storage. That's not a target. That's the floor. Their test machine's internal SSD sustains 12.78 gigabytes per second, a very fast drive. Divide 12.78 over 17 gives a Weller physical ceiling of 0.75 tokens per second on that hardware before the processor does a single multiplication. And their measured best, 0.63, which is 84% of the physical ceiling of the drive. Sit with that because it's remarkable in both directions. It means the software is nearly perfect. There is almost nothing left to optimize because it's already saturating the hardware. And it means no update will ever make this fast. Want 10 tokens per second, merely readable speed? That's 170 gigabytes per second of storage, which is roughly a dozen top-end drives striped together, at which point you've built a strange, expensive computer specifically to avoid buying a graphics card. They also tested the failure case, so you don't have to. The same container on a USB enclosure managing under 1 gigabyte per second. Run my division on that, about 18 seconds per word. Their documentation says it plainly. Put the container on internal NVMe. Now you know why that sentence is there. And one more speed the engine can't escape. The engine tries to predict which experts the next layer will want, and starts reading them early. But in their careful phrasing, the real router still makes the decision. So this changes timing, not the result. Prediction can hide some of the delay. It cannot change what must be read. For scale, 0.63 tokens per second is roughly 28 words a minute. You read at around 240. This is not a chat experience, and nobody involved pretends it is. It's an overnight machine. You hand it something hard and read the answer in the morning. The table that runs backwards. Now the reason this video exists. The obvious next thought, mine included, is fine, storage is the bottleneck, so cache more. Give the expert cache more RAM. Hit the disk less, go faster. That's how computers work. Their documentation contains a table of exactly that experiment. 4 expert cache sizes. Same machine, same model, same process. I'm going to read you all 4 rows. Cache of 3.3 gigabytes. 29% hit rate, 0.56 to 0.58 tokens per second. 17.3 gigabytes, 36% hits, 0.63. The best result on the board, 23.3 gigabytes, 38% hits, the hit rate went up and throughput falls to 0.07. 29.3 gigabytes, 41% hits, the best hit rate of all 4, 0.07 tokens per second. Read that curve again, more cache, better hit rate, fewer bytes read from disk, and the engine gets roughly 8 times slower. Every instinct says that's a misprint. It isn't, and their explanation is 2 sentences long. I'll read it exactly. The engine is inside its budget and the machine is not, so a cache hit becomes a page fault. Giving the process more memory is not always faster. Here's what that means in plain terms. Past a point, the expert cache is competing with everything else for physical memory, including the trunk the 27 gigabytes that must never leave RAM. The operating system, under pressure, starts quietly paging pieces of the trunk out to disk. And now the arithmetic turns vicious. The cache proudly serves an expert from memory, and the attention weights needed to use it have to be faulted back in off the same drive. The engine is already saturating. The hit rate climbs while the machine drowns. A cache hit becomes a page fault. That sentence is worth the whole repository. And there's a quieter finding in the same table that I haven't seen anyone mention. Look at the first row. Shrinking the cache from 17 gigabytes down to 3 costs only about 10% of throughput. The cache barely matters at the small end and is catastrophic at the large end, which tells you the working set of a model this sparse is so vast that caching is nearly hopeless anyway. The engine's real job was never to cache well. It was to stay out of the operating system's way, which explains the strangest design decision in the codebase, the one that reads like paranoia until you've seen this table. The engine deliberately bypasses the operating system's own file cache. On the Mac, a specific flag on every read. On Linux, direct I/O, on Windows, unbuffered files. It goes around the kernel on purpose on all three platforms because a cache the engine doesn't control is a cache that will eventually eat the trunk. Their storage benchmark even defines drive speed as random reads with the page cache bypassed, because any other measurement flatters the drive with memory the real workload won't have. The general lesson, and it travels far beyond this project. When you're operating at the edge of a machine, the operating system's helpfulness becomes the hazard. Every convenience layer between you and the hardware is making assumptions, and at the edge, the assumptions are wrong. The engineering culture, and today's confession. I want to spend 2 minutes on how this project documents itself, because it's the part that most changed my estimate of it. Their changelog states a policy I've never seen written down before, where a change was measured and not adopted that is recorded too, quote, because the measurement is the useful part, and they mean it. Buried in the backend documentation, a kernel rewrite recorded as 2 times faster on the kernel and 1.2% end-to-end, kept, with the disappointment stated, another change recorded flatly as 22% slower, and the reasoning preserved. A note that their fastest vector instructions have never actually executed in CI, with the sentence, a green CI is not evidence. And then this morning's release. Version 0.6.6, dated today, contains an admission. Their own disk benchmarking tool, the tool whose entire job is to certify whether your storage is fast enough for this workload, had been measuring the page cache on Linux. The very mistake the whole engine exists to avoid, sitting in their own measuring instrument, answering the question wrong for every Linux user. They found it, fixed it, shipped it, and wrote it in the changelog in plain language. Think about what that pair of facts means together. The central discipline of this project is, don't trust caches you don't control. And when they discovered their own ruler had been fooled by exactly that, they said so publicly the same day. You cannot benchmark a project's honesty, but you can read its changelog. And this one is the best signal of trustworthiness I've found in this repository, better than the validation suite, better than the star count, better than anything in the README. The part nobody's reporting, it can see. Here's a capability I haven't seen mentioned anywhere, sitting plainly in the documentation. The engine supports images. K3 is a multimodal model, and this engine carries the vision tower validated against its own reference to the 6th decimal place, same as the text path. And then the documentation does the honest thing and prices it. An ordinary image becomes 256 prompt positions. The vision tower itself is quick enough, but every one of those positions then passes through the full language model like a text token at their measurement, about 2.8 seconds per position. Do my multiplication, 256 times 2.8 is a little over 700 seconds, roughly 12 minutes to look at one photograph. I include that not to mock it. It's the same physics as everything else here, but because it's the perfect miniature of this whole project, a genuinely frontier capability on your own hardware at a price measured in patience. And because they publish the per position cost themselves, knowing you'd do exactly the multiplication I just did. The buried headline. Now the result that changes the practical answer, sitting quietly in the same benchmark table as the giant. The engine isn't K3 specific, and its second listed model is KIMI Linear, a 48 billion parameter model. The numbers from their table, a 19 gigabyte container, 1.28 gigabytes of RAM, and about 10.7 tokens per second on the same machine. Run the ratios against K3, a container 52 times smaller, a memory footprint 23 times smaller and roughly 17 times faster, which crosses the line from watch it think to actually usable. 10 tokens a second is reading speed territory. Their own README says it directly. If you only want to try the engine, start with KIMI Linear. And notice what 1.28 gigabytes of RAM means. That's not runs on a gaming laptop, that's runs on almost anything, with 15 gigabytes left over on even a modest machine. The same trunk and stream architecture, applied to a model sized for the hardware people actually own, stops being a demonstration and becomes a tool. A capable model, fully local, in the memory footprint of a web browser tab. The 2.78 trillion parameter number is why this project got famous. The 48 billion parameter row is why you might actually install it. Honest practicalities. 4 things before you try. 1. Internal NVMe is not a suggestion. You've seen the arithmetic. External enclosures turn seconds per word into tens of seconds per word. And check your free space, honestly, the K3 container alone is close to a terabyte. 2. Your SSD will be fine, and here's why. The objection you'll hear is that streaming 17 gigabytes per token will destroy the drive. It won't, and the reason is worth knowing. Flashware comes from writes, the program and erase cycles that damage cells. Endurance ratings are defined entirely on writes. This workload is almost pure reads, and reads don't consume endurance. Your drive will outlive your interest in this experiment. 3. The electricity is real. Keeping a laptop pinned for hours to produce what a hosted service returns in seconds means you're trading someone else's capital cost for your own power draw and your own patience. For most questions, most days, that trade doesn't favor local. It favors local completely when the material can't leave the machine, which is the honest case for this whole category. 4. This is young single organization software moving fast. Today's release changed a public structure in a way that breaks existing integrations, they say so clearly, but it tells you where this is in its life. Adopt it as an experiment, not a foundation. And credit where it's owed. This engine is not the first. A project called DeltaFin runs the same full model on a single machine, every token decided by K3 itself, with small draft models allowed to guess ahead and the big model checking every guess. Its published number on older hardware is around 0.28 tokens per second. So the fair statement is, this engine is leaner and roughly twice as fast on newer silicon, faster and leaner, not first. Two independent teams landing on the same trunk and stream shape within weeks tells you this is where the physics points, not one person's trick. The honest limits. 4. 1. Every performance number here is the project's own measurement on their machines. I pulled and read the documentation. I did not run a terabyte download. The validation methodology is unusually strong. Layer by layer checks against a reference implementation with the criteria published. But strong self-validation is still self-validation. 2. The floor is context-dependent and the fine print is the truth. 29 gigabytes opens it at short context. 64 is the stated practical minimum. The title's 32 is the uncomfortable middle where it runs and pages. If you take one number from this video, take 64. 3. Quality of the compressed experts is the open question. 3 bits per weight is aggressive. The end-to-end outputs match the reference implementation to floating point noise, which is genuinely reassuring, but independent quality evaluation of this specific conversion doesn't exist yet, and matches the reference and as good as the original service are claims of different sizes. 4. This is an ARM-first codebase, and their own documentation notes there's no x86 vector code in the engine. If you're not on Apple Silicon or comparable ARM hardware, read the backend documentation before assuming your machine is the machine they measured. Step back, because there's one idea under all of this. The fastest consumer drive on Earth caps this model below 1 token per second forever. The software is already at 84% of that ceiling, so by every conventional measure, this project is finished. There's nowhere left to go. And yet, it's the most instructive repository I've read this year, because what it actually demonstrates is that the boundary of what runs on your hardware is not a fact about your hardware. It's a fact about how much of a model must exist at once, and that number has been collapsing all year. Not because machines improved, but because someone kept asking what's actually awake in there. A database company looked at a 2.78 trillion parameter model and saw a storage layout problem. The result is the largest open model ever published, arriving over a torrent link, opening on a laptop and telling you in its own documentation, in plain sentences, exactly where it's slow, exactly when more memory will hurt you, and exactly which mistake they shipped in their own measuring tool this morning. Every part of that is only possible because the weights are public. You cannot write a custom engine for a model behind an interface. You cannot lay out its experts for one read apiece if you've never seen them. Permission to look inside is what turns impossible into slow but yours, and slow but yours for the things that matter beats fast but theirs. So here's my question, and I'll pin it below. Run your drive's numbers. You don't need to download a terabyte to participate. Benchmark your internal drive's sustained sequential read, divide 17 by it, and post the tokens per second ceiling your machine would have. That one division tells you more about your computer's future with large models than any spec sheet. And if you actually run either model, the giant overnight or the 48 billion one at reading speed, post the hardware and the real number, because a public map of this is worth building and nobody has built it. And the softer question, what would you actually hand a machine that answers overnight? Not what's impressive, what's useful at that speed. The answers to that decide whether this whole category is a party trick or a tool, and I genuinely don't think anyone knows yet. Every link, the engine's repository, the exact documentation pages with the backwards table, and today's changelog, the sibling model, the prior art, and the model's own weights and terms is in the description. Check my divisions. That's the entire point. That's the standard here. The real explanation, sourced in plain English, with the arithmetic shown and the fine print read out loud. If you'd rather own your tools than rent them, subscribe. That's what we do every single day. I'll see you in the next one.